So it's my great pleasure once again to introduce Mr. Andy Rayner, Chief Technologist from Nevion, a Sony Group company. And Andy's going to be talking about timing planes in IP production, both linear and nonlinear, which is very important for a lot of our cloud-based future. So take it away, Andy.
Thank you, Wes. Good to be back with you. Glad there's 2 or 3 more people here than last time. Anyway, it's good to be with you on this first morning or lunchtime of IBC 2022 and see everyone back together again. As I said previously, and because it's the day after very sad happenings in the UK, I wanted to pay my tribute to Her Majesty Queen Elizabeth II as I start this just for 10 seconds. This is the only picture I have of myself and the Queen. This is back in 1977. You can see me there highlighted in the blue line talking to the Queen. Anyway, that was a long time ago. Jumping back in to what we're talking about today, I want to talk about linear connection-based signal flows and non-linear compute-based data flows and the challenges we have in the timing ecosystem with them. And there are 3 things I want to consider as headlines, and I'm going to unpack different bits about these as I go through. Capturing time, tracking time, and optimizing time, and just reflect on some elements of all of those. And I'm also going to reference, as I go through, some of the work that's happening specifically on SMPTE ST2110-11 on tracking time in linear IP production workflows, but reflecting on how that works. If you haven't already seen it, and if you weren't here a minute ago in the actual theatre, then some of this is tying into the work being done by GCCG in the VSF activity group. So there was a talk just previous to this. So if you're on watch again, then do check that out, because we're actually, I'm relating to some of that in where I'm going with this talk. Okay, so the linear journey for how we do standards in IP production is roughly like this. These are the various contributing standards that have influenced what we're doing in ST2110. And as a result of that, we have a suite of 2110 standards. The top 2 rows are the data plane, and the bottom row is effectively the control plane, which is the NMOS standards. That's all very well and lovely, but I'm going to talk about the kind of the legacy that ST2110 has inherited in a minute from a timing perspective, but also jump to one of my favorite pictures I've been using for the last 18 months in presentations, which is this presentation, this slide here. And the reason I want to show this is this helps to articulate the mindset of where I think we're heading as an industry. And there are a few fundamentals here. So first of all, the acquisition, that is the capture of the video and the audio, is always inherently going to be a real-time process. There is a shutter on the camera. Hopefully, we're not just shooting at 50 or, in strange countries, 59.94 frames a second, but maybe in the future we're going to be up at 100 or 120 frames a second capturing those images. Similarly with the audio, we tick our sampling clock at 48 kilohertz, or if we're very precious about it, 96 kilohertz to actually acquire that audio. That's always going to be a real-time linear process. Then shoot to the other side of this picture, the consumption. The consumption is always going to be a linear process as it hits you as a human being. So regardless of where that's constituted, whether it's on your mobile phone, your tablet, or your lean-back television, or any other viewing device you're looking at, it's reconstituted as a linear flow of video and audio for you to consume. And then there are human beings that are involved in the creative production. They're in the gallery, they're in the sound booth. Those guys and girls all need to actually see and hear those video and audio flows in real time as part of their involvement in producing it. However, aside from those elements, the front end, the back end, and the humans involved in the production, there is no reason why our actual chain of data that actually constitutes those elements needs to be constituted as a continual linear real-time flow of data throughout the rest of the system, or is there? So we'll come on to do that, and I want to unpack that. But there are one or two things that have actually made us make the decisions that we have, even in the recently formed and even more recently updated 2110 suite. So first of all, we've done a few things as we've inherited this linear legacy of the last 90 years of broadcast. The reason we've done that is because we've tried to be compatible in the thinking and the way signals have flowed. And in SMPTE 2110, we've actually specifically for the linearity of the data specified there's a part of the standard called -21, which is quite complicated yet quite fun at the same time. And the reason -21 exists is because we have to maintain packet integrity. And if we don't put the packets in a nice linear manner, then there is a risk in certain switch fabrics, depending on how deep their buffering is, that we will lose packets. And why might we lose packets? Because they are UDP packets. They are RTP UDP packets. RTP and UDP are wonderful. They are the mainstay of how we do real-time media flow on IP. But they do have a challenge in that there is a lack of guaranteed integrity of them getting through a system. So most of the packet transactions that you're used to on your phone or on your computer are TCP. That has a handshaking mechanism that actually says if the packet doesn't get through, I'm going to request it again. So inherently, the system underlying you guarantees that you get through there. UDP doesn't do that, but because of that, it's fast. And because of that, it's actually quite easy to actually run and make happen. There are other technologies, some are vendor specific and some are non-vendor specific, that actually attempt to do somewhere between the two. They attempt to actually give us the integrity that TCP gives us, but actually in a more time efficient manner than TCP can work. But we'll come on to that in a minute. And what's been alluded to in the previous presentation is the concept where we actually are looking in a compute-based future, as I was alluding to that simple picture I showed you a couple of diagrams ago. We actually want to be able to deterministically transfer data between compute instances. So we need some kind of media mapping. Then we need a deterministic data transfer function and another media mapping that comes where we abstract that back out. Now, there are technologies that have been used to do that. I'm just gonna move forwards here. So we have in the RTP UDP space I've been talking about, we have methods by which we protect that. They're all ways of actually getting round ensuring we have integrity whilst having a non-deterministic transfer function. So we have spatial diversity of packet replication and merging at the RTP layer, which is what 2022-7 is. We have effectively sending extra packets to actually allow us to heal missing packets at the far end, which is what FEC is. And we have ARQ, which is effectively a transmission re-request function. It's kind of the opposite polarity to what we do with TCP, in as much as there's not a handshaking on every packet. There is a, I put my hand up to say I haven't got a packet. And then there's these underlying technologies below, which actually all in their own way actually make sure that you get the packet, and that they are either involving positive handshakes or negative handshakes, and multiple other ways of actually ensuring those get through, effectively ARQ mechanisms that are happening underneath the skin. So that's deterministic data transfer, and specifically calling out, as it's the obvious one, AWS a year and a half ago announced CDI, and that makes use of their SRD technology under the skin, which is a combination of multi-lane transport and mini ARQ stuff that's happening below the scene. But fundamentally, from the perspective of the end user, it means we actually have a guaranteed data transfer function, hopefully within a reasonable time-bound nature. So just bear in mind those concerns, or those issues, if you like, about that we've created with our linear workflow and what we've created with 2110. As we look at in 2110 what we've been, some of the challenges we've got with timing per se as it stands. So One of the things that I think I was relatively naive on as we were developing the 2110 standards was that the origination time would be propagated through the system. So we would actually have the ability to know at any point within the workflow what the relative time offset between different media essences is. Now, unfortunately, wisdom retrospectively is always very valuable. We weren't explicit enough in the way we define things to actually encourage that as a behavior. So what we actually have is a number of functions that sit together in a concatenated processing signal chain. Each of them currently has the ability to propagate origination time or not to do so. So if you think at the front end, as you can see on the left-hand side there, you have the microphones, you have the cameras, and they actually inherently, by the way 2110 is defined, have an RTP timestamp that relates to the absolute moment at which that content is actually captured in the real world. We then have a number of devices in the chain which may or may not keep that timing information as they process. Now, there has been some work done in the revisions of SMPTE 2110, specifically to the -10 element, which actually tries to encourage and recommend the ability of the propagation of that timing information. So we have what we call a preserve capability. So basically, any device downstream of that acquisition device, which inherently is giving you absolute time on its initial timestamps, any downstream device is able to either be a regenerator, so it will give a new timestamp, which means you've lost the original information, or it can be a preserver and it can declare such. So it actually, if you like, what that means is video frame N egressing that function has the same timestamp as video frame N had when it ingressed that function. Similarly, for audio would be, the audio sample N egressing that device would have the same timestamp as audio function, the sample as it was ingressing that device. But we have this mixed economy of these preservations or non-preservations as we go through. We're going to talk about that just in a couple of minutes. This is a picture a friend of mine called Prin drew when we were trying to think about what are we needing to do to actually understand timing through a whole system. And this is a quite complex picture, and I think it was intentionally drawn to actually draw attention to things, because what you've got is a ripple, if you like. You've got a number of processing devices in a chain. Each of them consumes some time to process something, and it actually then ripples through. So you actually have an accumulated time offset that actually is incurred, or time delay, if you like, through a processing chain. Some of these may be very quick, some of these may be short, and I will just call out now, I think in the 2110 world, we've made things a little bit more difficult for ourselves due to the fear of how we actually handle timing offsets. So in an SDI world, as an example, most vision mixers in the SDI world now probably have 1, 2, or 3 lines of delay to the video going through a multi-ME vision mixer of a modern variety. Typically, a vision mixer that's actually implemented in 2110, because people are scared of TR offset, we actually simply just add a whole video frame of delay in a vision mixer to come back to an exact timing point. So we're actually adding more latency in a 2110 world than we used to add in an SDI world to do the same thing, which is a challenge in itself. But that was a side note really to this diagram. That wasn't the point I was trying to make. We've got this ripple of added latency. We also have, just calling it out specifically on a separate diagram because it was difficult to see buried within that picture that I just showed you, we also have the effect that some sources, video sources for instance, are actually used at multiple points within the downstream timing. So you've actually got a source which is being consumed in what I call multiple timing planes. Talking of timing planes, I'm going to just confuse you like crazy with this diagram. This is my attempt to actually show a whole load of different timing planes. It's not supposed to be relational, but it's an attempt to show you the different things that can introduce delay in a system. Some are intentional, some are by design, some are equipment processing, some of the law of nature on what you're actually trying to do. So, for instance, we've already talked about a production switcher. Typically, in an SDI world, one line delay. Typically, in a 2110 world now, that gives us 1 frame delay because we're scared of TR offset. We have remote control surfaces, such as were used from people's domestic dwellings during COVID. And inherently, there's a latency on that because you're using typically public internet connectivity to get to a home and then back again. So you could be talking about at least tens of milliseconds in a round trip delay that you're incurring by doing that. So everything downstream of that point in the production needs to actually compensate by having a timing plane that exists that can accommodate that round trip delay. We then have what I think is a really good example, remote commentaries. More and more people are doing remote commentaries, again, from people's domestic dwellings. People are sitting there viewing a compressed proxy of a video. They're doing the commentary in a specific language, and then that's being fed back. And if you're creating a compressed proxy, then going over public internet, you're then taking someone's commentary and pulling it back over public internet to pull it into production, which is what's happening all the time. You could be talking about hundreds of milliseconds of delay that you're incurring into the process because of what you're trying to achieve. And your end production time has to allow for that because that's something you're adding in. Similarly, profanity delays, that's something that you're adding in to help you manage the program, and you may be choosing to add 1 second, 2 seconds, 3 seconds of delay, of latency, intentionally just by buffering everything into the system so you can actually weed out profanities that are in the system. We also have here as an example augmented and virtual reality systems. So it's amazing how the creatives in a production chain, whilst they abhor unnecessary latency, if you can actually make something that gives added creative value, like a VR system or an AR system, then they will tolerate many but of delay. And typically, some of these VR and AR systems may cost you the order of half a second's worth of latency, but by the fact of what they're doing and the way they're rendering and doing the production. So you've got different timing domains. And in fact, talking about the VR system, this next diagram shows this very well. This is a real-world use case I was talking to people about from last year. The VR system cost 200 milliseconds. So you've actually got some cameras that are actually part of the VR system that are actually offset inherently as they come into the main production switcher by 200 milliseconds compared with everything else. But how do I know what that timing domain is, and how do I track it? So hold that thought, because we're going to come back to that shortly. But I just want to give a little plug, as I mentioned previously, to the work that's happening in VSF on the ground to cloud, cloud to cloud, cloud to ground. So there are two fundamental parts of this work. Again, I'll refer you to the previous presentation that Kieran and John did to give you the detail. But there's kind of the linear real-time bit, which is that red up and down. Typically, that's a real-time delivery of data in and out of cloud infrastructure. But the cloud infrastructure itself, going from compute to compute, is something that inherently doesn't like to be linear. Computers don't do linear very well. We have to put a lot of effort into linearizing streams, especially to conform to things like SMPTE 2110-21 when we come out of compute. And arguably, that's very unnecessary as we move to a more concatenated all-compute world, because inherently, as long as the timing information is preserved in a way that allows us to do what we want at the end, we don't need to be in this pristine linear data handoff. As long as, going back to my UDP RTP thing, as long as we're not losing data as a result of going non-linear. Jumping back to what I was talking about, the inheritance we've had of the last 90 years in terms of the way we have done video, the raster scan. I mean, before this was a mechanical scan, I guess, but the raster scan was there in the 1940s. And that is what we've inherited. And largely speaking, if you look at the ST2110 standard, there's a fair amount of it has actually still been driven by and is an inherited elements of the raster scan, even to the fact that some of the timing models we've got allow for effectively the flyback of the raster as it used to be. I mean, no one uses this anymore, or hardly anyone. I don't think anyone's probably got a CRT in their home anymore. So this is, if you like, a legacy that we're still running with. But that's what has driven even things like ST2110. So the question is, do we want to try and leave that behind as a technology, as an inheritance, to actually help us to be more forward-looking in the way we do timing at the moment? So we've already said that computer doesn't do linear data handoff very efficiently, but also compute processing is inherently kind of a non-linear function. So we have this distribution curve here. You know, the execution time of a software function is nominally going to take a certain amount of time, but there's a tail. So if we're actually trying to compute time and work out what's going to happen, we actually need to allow for, in our arbitration, the worst possible time, or the longest time that function is going to take. And I'm just going to show again one or part of a diagram that John showed in the previous presentation from our GCCG work, where we're actually looking at what the impact of concatenating those timing functions. So if we have compute that executes in a certain amount of time, you know, those of us that are used to FPGA-based infrastructure where we actually know this takes 5 clock cycles and then we're popping out, this is a much less deterministic thing. But there are some bounds we can put on it. So thinking of this diagram here and moving forward to this concatenation diagram here, what we have in the mind, if you think, as we orchestrate and actually accumulate the timing of a process of compute functions, we actually have this T1, T2, T3, 4, T5, etc. All of those, we need to bound it. See, in a traditional piece of an appliance that's used in a broadcast function, you would have a number of milliseconds or microseconds that would take. In a compute function, we have, you know, an execution time, and we're very confident. We have a high level of confidence it will take n milliseconds to actually execute that. So we actually can build up an orchestration model that actually allows for that worst case compute timing as well as we go through this. So this is kind of showing you that original picture I had done for linear video, but actually thinking of it with virtual compute functions as well. So we don't have that nice, T processing or T proc time that's a magic and deterministic number that exists for each of these, but we do have this T max. A worst case time that compute function is going to take to execute that. And we can actually use that in conjunction with the other timing information that we're pulling together to still actually create a legal and usable use time on the right-hand side. And the other thing to say, which is was brought out a little bit in the last presentation, but I'd like to highlight it, is that the most important thing in this nonlinear compute timing model is that the capture time, the origination time of all of those media elements, the video frame, the audio sample, has to be perpetuated, because as soon as we go nonlinear in the way we actually handle data downstream, as soon as we go nonlinear, we potentially lose the relative time information. So absolute time information becomes completely imperative rather than just nice to have. So we have these two elements here where we've got absolute time and relative time that we need to actually make use of. I think I'll jump through this because these two elements are not too important for me to talk about here. So coming back to where we're looking at the piece of work which we're doing in 211011 at the moment, which is attempting to pull together this traditional linear world, which is what we set off to do, but we're now trying to see whether we can embrace this non-linear timing world as well of compute. So basically you can see some devices here that are linear devices, as I would say, and some that are non-linear. We're trying to work out an ecosystem that actually has timing information that allows us to on a timing preservation that is going to happen hopefully more and more in a 2110 chain, as I talked about earlier, but have a control system that's actually able to ask and query and determine the processing time of both linear and non-linear processing elements in a chain, along with the link time, the propagation of the data between those functions. So the control system will be able to do the math and accumulate the relative timing processes, that are the time that's taken by the processes and the transits, to actually give us the ability to actually automatically equalize and accommodate the timing information at each point. So fundamentally, this is kind of in two boxes what the ecosystem looks like: a control system that does the coordination, and media devices that are savvy to actually be able to do that. And just linking it into AMWA, NMOS work as well, we think this potentially is a key first use case of the parameterization and control stuff that is being looked at in NMOS, and you can hear more about that from other people coming up through in the next couple of days. This is the wording of the SMPTE standard that we're looking at. And again, I think we've probably covered what I was going to say in that diagram. So I'll jump to here as I draw to a close. So capturing time is really important. It's important to understand what happens there. It's important not only to capture that time, but to propagate it through the system. If we can't propagate it, then we need to be able to query sufficient information to work out what the propagation times are and be able to track it through the way we do that. And then optimizing time is something we need to actually handle. I'll do some more talking about that in another presentation another time, to make sure that we actually optimize the way we hand off, rather than doing these integer frame latencies that we're actually starting to incur just to accommodate things easily. So we need to be not scared of TR offset. We need to be not scared of having timing offsets, which we present within our system, and also slicing and dicing frames so we don't hand integer frames worth of data. So do come and have a cup of tea with now, or if you're ever in the UK and want to call me up, I'll happily come and meet up with you for a nice cup of tea wherever you are.